That's good to have, right? First, okay, right? First, teachers, okay, right? So to all the teachers out there, right? It is important that you see this, this journey as something that you should take together with your students, okay, right? Because yeah, take pictures, okay. Tell the teachers, okay, you should, right? The teachers should be following closely with the students, okay, right? Because along the way you'll find that there's a need for you to teach them a lot of things, okay, right? Like for example, next thing is the idea of a scientific method, right? So I'll not elaborate what scientific methods are, okay. In fact, later on along the with my talks, things that I tell you to do or to watch out, right? They are part of this idea, okay, right? So equipment to have high-speed camera, okay, right? You can get high-speed cameras of 1,000 frames per second for less than $1,000, okay, right? And then tracker, right? This is the this is the link, right? Where it's a program, right, that allows you to analyze your whatever you have taken, whatever pictures that you have taken with a high-speed camera, frame by frame, okay, right? So, and then for mathematical tools, right? For softwares, right? Mathematica or Python, okay, right? So, rough sketch of what a scientific method is here, okay. So I'll not say anything. But lastly, attitude, okay. Now, what I'm going to see next in the next few slides, right? I'm not going to be soft-hearted, and not show you equations. So there will be equations, right? So attitude, right? Make everything as simple as possible, but not simpler. Okay, right? So okay, you're not going to vomit, right? Okay, right? So let's look at the first problem, right? This is a Cat B problem, right? The statement is construct a passive device, right? In other words, okay, right? And all these wordings were, after some discussion, okay, among the international organizing committees, right? Passive device, so you cannot think about, having a motor, right? And then you have a propeller, right? Powered by a battery, right? And then your egg never hits the ground, okay, right? So, no, passive device means you just live on its own, okay? Right, that will provide safe landing. Safe landing means not cracking the egg, okay? For an uncooked, okay, hen's egg, right? Not fish egg, not duck egg, hen's egg. Okay, when dropped onto a hard surface, okay, right, and then from a fixed height of 2.5 meters. So this one I put in red, okay. The device must fall together with the egg, right? So you cannot put something at the bottom and then drop the egg, fine. Okay, right? So, and then what is the smallest size of the device you can achieve? Okay, right? So, smallest, right? If you have an egg, right? And you can find an atomic size particle that you can attach to the bottom of the egg and you throw, okay? And that atomic particle is able to make the egg not crack, okay? Right? Then you win. Get it? Get the idea? Get the idea? Okay? Right. Okay. Right. So, when you look at this problem, right, I'm not sure how many of you were thinking, okay, so trial and error. Okay? Right? I try this, I try that. Okay? Right now, there's nothing wrong with that. Okay? But remember, this is a physics competition. Right? So, you have to do, right, before you devise anything or think about some gadgets that you want to make, right, do a preliminary analysis. Okay? So what preliminary analysis are we talking about? I'll make use of this problem, which is simple enough to illustrate some of these points. Okay? Right? So 2.5 meters. I'll drop the egg later lah. Right? Okay? I don't think this is 2.5 meters, maybe slightly more. Okay, right, then you drop, right? So the egg will go down to the floor, right? And then, how does it crack? How does it crack? Huh? Right, it cracks because it's smashed on the floor. Okay, I don't know. Alright, so you have to think about this. Okay, so you just now Marcus said, you have to I'll give you papers, you go and read. Yeah, right. That is if you have a paper on this, fine. If you don't, then how? Right? In fact, this problem you can find it in the internet. There are many people playing with this, school projects, right? But I don't think there are any papers that discuss this. Okay, right? So how? Right. So in this case here, you would have to. Right. This is where if particular students have never been introduced to ideas of force, impulse, momentum, right, and things like that. This is where the teachers may have to come in. Okay, right? Feed them with some preliminary ideas. Okay, so that they can begin. Okay, right. So in this case here, if we look at how the egg gets cracked, right, it has to do with right, the fact that if you release the egg, right, if we assume that it's going to be freely falling, in other words, no air resistance, okay, when it reaches the floor just before impact, right, it will have a certain momentum, okay, given by this, okay, right, and so with the fixed height 2.5 meters, okay, you can actually calculate, right, if you estimate the mass of the egg to be 50 grams, right, then the momentum is about 0.35 Newton second. Okay, right? So this is the momentum just before it hits the floor. Right? When it hits the floor, you come to rest. Right? And when it comes to rest, from impulse momentum theorem, we know that there must be a force that allows this change in state of motion. Right? Okay? Right, so from here we can estimate, if we estimate that the time it takes for the egg to stop, okay, that means to go from this linear momentum to 0 is say 1 second, this will be the force experienced by the egg on the average, okay, on average over 1 second. Average over 0.1 second, 3.5 Newton. 0.01 second, 35 Newton. Okay, right, typically the impact time is this. It will be 350 Newton, right? For an egg, right, to crack it, if you load the egg, that means, if you have a tray of egg and then you put loads on it, okay, right? So which is different from impact. But if you keep loading, what happens is that about 35 Newton force, right, will crack the egg. Okay, so this time is critical. Okay, so if you are able to lengthen, if you are able to lengthen the time, right, between coming from with this linear momentum to 0 linear momentum, then you will be able to prevent the egg from cracking. Okay, right. So basic physics like this, you should have. Okay, right. Now next thing, right. This is a simple problem, okay, and maybe very cheap to to conduct, right. You may be thinking, okay, I'll create devices. Like for example, if you look around on the internet, half of the time you will see people coming up with the idea, I built a propeller, right? I put a parachute, okay? Right? What do you think they are doing? They're trying to slow down. In other words, right, to take away this assumption. That means, you create a situation where air resistance is important, okay? Right? So that by the time when the egg reaches the floor, right, the velocity will be smaller, so the momentum will be smaller, okay, etc., etc. Okay, right. So therefore, and then the other half, okay, of the proposal will be something like this. Right, I build a cage, okay, I bubble wrap, I put it inside my shoe. Okay, right, things like this. Okay, right. Which proposal should you consider? You can actually do a calculation. Okay, right. So if we were to do air resistance, then the maths gets a little bit complicated. Okay, but you can analyze, or this is where again, I said teachers will have to come in. Okay, I use Mathematica. Okay, I've checked that this is correct, and then right. So this will be, roughly the K value that you need for the air resistance. Okay, if you assume air resistance to be of this form, okay, this will be the K value, right? Then you have to ask, if I need something that has this K value, right? then so that when it comes to the ground, okay, the momentum is 0.035 Newton second, right? This will be the K value that I need. If you design something, what will be the size of a parachute? Such as over 2.5 meters, okay, you will come to this momentum. Right? That is why if you look back at the question says smaller size. 2.5 meters. Okay, so these are the constraints, okay, that you have to take into account. Okay? Right. Then of course you will say parachute should be air drag, it should be of this form. Okay? Right? And in this case here, if you work through the math, okay, again, you can work out, right? This is the K value, 1.0. Okay? Which will mean that your parachute has to be then bigger. Okay? And it has to be open. Right? Because 2.5 meters, what is the time taken for the egg to go to the floor? Huh? No, not 3.6 seconds. 3.6 seconds only if K equals to 1. I'm saying in free fall. You can work out, right? Okay, I didn't work out the time, so I cannot tell you the time. But I can tell you the speed. If it is free fall, when it hits the ground, the speed is 7 meters per second. 7 meters per second. How fast is 7 meters per second? If you run around 2.4 meters, 2.4 kilometers, your IPPT, 2.4 kilometers, right? About less than 6 seconds. At 6 minutes you'll finish. Okay, less than 6 minutes. So the egg can run faster than you. Okay, right? So in this case here, preliminary analysis will tell you, right? Perhaps you should be considering this type. Okay, right? So yeah. So that's some of the things that you can do before you actually start your experiment. Now, how do I know that an egg cracks at 35 Newton? This one you can look up the literature now. So I will give you one paper. Right, I'll give one paper that studies impact of eggs, hens egg. Okay, right, and yeah. So this one is the only paper I'll give you. The reason why I don't give you more is because depending on the design, right, you may need different reference papers. So you can maybe talk to your teachers, right? Can send me an email, and then we'll see if you cannot get access to the papers. Okay, right. Problem number 2, no paper. Okay, so for the egg you have one paper. For problem number 2, balloon air horn, no paper. Right, so in this case here, I'll just give you, right, I think later on, right, if you like, you may come and take a picture of how this is built. And this is more respectable. Right. So so in this case here, well, you know, in the spirit of like science, if you look at these things, right, you may be thinking of analogous, like, you know, the horn speaker, right? So if you want to analyze this, you may tear this whole thing apart, right? It's basically made up of this membrane, right? And then the rod, as well as just this tube, okay? Here, it is important to have airtight, okay? Then that's about it, okay? Right, later on, if you want to play, you can play with this. There is something here that you can play with later. Right, this is more powerful. Shall we try it now? Okay, right, hey, while you're playing with this, right, okay, remember, remember to vary the few things and then you try and see for yourself, right, what is actually producing the sound, okay, yeah, right, okay, I think I'll leave you to make your own observations, okay, right, for example, just now, one of it, if I push this back a lot, right, no sound. Okay, right, because it is actually telling you something. Okay, right, so when you get, right, the experiment's not working, right, don't just say, oh, it failed, finish. Okay, right, because why it fails actually will tell you about the mechanism behind producing, you know, the sound production. Okay, right, hint, yeah, right, and then the other thing is that, as I said, the theory, if I don't give you the theory, right, it's because you can actually discover it, okay? You can take the pipe, for example, this is a bigger scale. This is a bigger scale thing, you know, right? If you have a bottle that's empty, right, you can blow air past it and you can produce a sound. Okay, right? So are the two things related? Right? Questions like this. Okay, right? So okay, so share with your teachers. These are things that you can discuss when you are, you know, playing around with this. Okay. So if you like to take pictures of how the thing is set up, okay, you can do it later.